Hi everyone. Uh, Today I'm going to proceed with uh, the next unit of this course, which is Unit 10, Basic Statistics and Assessment. So this topic is quite important for you to be able to interpret your students' score or marks in your assessment. So in this unit, should be able to explain the meaning of a little bit about the measurement of central tendency and also the measure of variability of a sample score. Okay, and also we can determine or calculate the mean, mode, and also median, variance, and standard deviation of data distribution or your students' score marks or marks. Okay, and then we also can describe the distribution of data using the measure of central tendency and also the appropriate measure of variability. Right, so with this statistics, you can assess the achievement in your classroom or your test later in terms of measurement and also the test. So, okay, so we look at the measure of central tendency first. Okay, this thing, I think you learn this in Form 5 actually. So a measure of central tendency is actually a statistic that describes the middle value that represent the entire set of data. So in another way to say this, we want to look at where is the data being mostly can be found. Usually it's in the middle, can be somewhere else. So we are trying to see where is the tendency that you can find the value of a set of a data. So normally we use a few measures for central tendency, which is the most common one is mode, mean, and also median. Okay, so what is mode? Mode is simply the measure we try to determine which score is the with the highest frequency. Okay, for example, here this is a raw score 1, 2, 2, 2, and 3, 3, 4, 5, 6, 7. So you can see the number 2 or score 2 is the most reoccurring score. So we can say that, okay, so score 2 is having the highest frequency of 4. Therefore, we can say that this score 2 is a mode for this set of data. Sometimes we can face a distribution of data with two modes. So we call this a bimodal, which is referring a set of score that have two values with the highest frequency or with two modes. Okay, for example, here you can see that 2 and 3 is 2 and 3 is having uh, same frequency, which is 3. Okay, so we can say that this bimodal, the mode is 2 and 3. So this is usually representing that your data have two modes. Okay, all right. So for group frequency distribution, in which that you have your distribution is being grouped according to intervals, so you can use this formula. Okay, so don't worry too much on this formula. We're not going to test about this, but at least you can calculate mode by yourself. So what is LMO? LMO is the class limit for the mode class. Okay, and the frequency D1 is the frequency between mode, class, and frequency difference between mode, class, and the class before the mode class. And then D2 is the after one, after the difference between the after class from the mode class, while W is the class size. Okay, so this is an example how to calculate the estimate, actually the estimate mode for group frequency distribution. So for example, here you have class limit, for example here 60 to 65, 66 to 70, and so on. So this is the class boundaries also given here. And then there are the frequencies here. Okay, right, this is a frequency. For the first class limit, the frequency is 3, second class limit will be 10, and so on. Okay, so this is the formula. And then the LMO, which is referring to the lower class limit for mode. So you look for which class limits have the most frequency. So you can see here, this is 20, the most frequency. So the class limit, the mode class is 71 to 75. So the lower limit for the class mode is 71. So this is 71. Then the D1 will be the difference between class before the mode class. So here the class mode is 20, the class before is 10 for the frequency. So you minus 20 with 10, so you get 10 here. Then D2 is the difference between the frequency for the class after the class mode. And then, so this is 15 here, so 20 minus 15, so you can get 5 here. Well, and then after that, this is the width of the class. Okay, so we just take 75.5 minus with 70.5, so you can get 5 here. So the mode, okay, 71 plus 10 over 10 plus 5 times 5. Okay, so you can get 74.35. So the mode here is being estimated as 74.35. So does it make sense? Yes. So the mode is that you estimated 74.35 is somewhere here, okay, in the same class. All right. Then mean is actually average. So usually the symbol for mean or average is X bar. So you have to remember that mean is a calculated middle value to represent a data set. So it's not actually uh, a real score. It's not a score from the data set actually, right? So if you have you want to calculate the mean for ungrouped frequency distribution, so you just use this formula. This is very straightforward formula. So X bar mean is equal to the sum of all the score divided by n. So n is X bar is mean. Okay, sigma xi is equal to total score. So n number of sample. Okay. So here's an example here. The test score for 5 students are 55.3, 75.5, 48.7, 68.5, and 68.9. So find the mean of this score. So you can just add all of the scores and divide it with 5. So you can get the mean score is 64.16. So you can see here 64.6 is not a actual score, but it's a value that is being calculated to represent all of this data. Okay, for sometimes there's a lot of scores, then it can be, you can see there are recurring test scores here. So this is still a mean group ungrouped frequency distribution. So for example here, for the score 58 here, okay, the score 58 here, you find it 11, the frequency is 11, meaning to say that 11 students with score 58, right? For example here, only one student, Okay, one frequency, one student with the test score 88. Wow, you can see there's a mode here. Okay, so there's 18 students here with the score 60. So if you want to calculate the total score, so you have to not divide, you have to multiply with the test score with the frequency. So 58 times 11, you can get 638. 60 times 18, you can get 1080. So then you can add all of this, and you can have a total score there is 4,645. So to calculate the mean, divide the value here, 4,645 divided by the number of frequency, which is 69. So you can get 67.32. So the mean for the test score of 69 students is 67.32. Okay, for if you have to calculate the group frequency distribution, okay, if you have too many students, like 200, 300, maybe you have to group the frequency. Okay, so this is the class limit given. So this is the frequency here. So you don't know actually what is the score. You only have the classes here. Okay, so the only way is to estimate. So you have to calculate the class middle point. Okay, so for this first class, okay, so the midpoint is 55, 5.5. For this one, 15.5, and so on. So this is middle point. So this is representing the score for this interval or these classes. Alright, so you just to calculate the mean, so you just multiply the frequency with the class middle point. So you can get here, for example, 25 times 5.5. So you can get 137.5 and so on. So after that, you just add. Here you can get 5,069. So you divide 5,069 divide with 138. So your score, the mean score would be 36.73. Okay, so where's 36 around here? So it does make sense because it is about at the middle. Okay, so this is the way you're going to calculate for mean for group frequency distribution. Okay, for median, right? So median is a score. Scores located in the middle of a score, a set of score that are arranged in ascending or descending order. So it can be determined by dividing a compiled set of ungrouped score into two equal parts. Right? So the median is actually the 50th percent score, okay, which is a score in dividing the distribution into two parts. Okay, and then the median is the middle value. Okay, the actual value, the score. And then if the score is even number, so the median will be between the two scores. Okay, so I will show you the good thing with median. It doesn't affect it with extreme score, unlike with mean. Okay, so for example here, if you want to determine a median for number of odd score, okay, here you have odd number of scores. So this score is already being arranged ascending. So the median of the above distribution is the score in the middle, which is the fourth score. So you have 1, 2, 3, 4, 5, 6, 7. So 7, your middle position would be the fourth one. So 1, 2, 3, 4. So you can say the median value is 61. Okay, It's quite straightforward for that one. If your set of data with even number score, so we have a bit of calculation. Okay, for example, here now we have 24 scores. So you divide 24 with 2, so you can get 12. Should be 12. But since 12 score is an even number, okay, so you're going to have a problem there. So you need to calculate. So 12 and 13 will be somewhere in the middle. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these two here. Alright, if you take 65, it's not really in the middle. If you take 66, it's not really in the middle. So it's between 65 and 66. Alright, so in order for you to estimate the median, so you divide that 65 plus 66 divided by 2, so 65.5. So your median is over here in the middle here. Alright, again, this is not a real score, but it represents these two scores, 65 and 66. Okay, so that is median. Well, this is the part that we always doesn't like, which is the median for group frequency distribution. So this is the formula. You don't have to remember the formula, but you just understand it. So what is L? L is usually lower class boundaries. Okay, this one is boundaries. This is referring to boundary. N is the total frequency. F, the capital F, would be the cumulative frequency before median class. F is frequency of the median class for F small f. And then the C will be the class size of the median class. Okay, we look at this example. We have the class limit over here. Okay, 31 to 35, 36 to 40, and so on. The class boundary is also given. Okay, and the frequency. And this is the cumulative frequency, meaning to say that you can get 6 because you 2 plus 4, 6, 6 plus 8, you get 14, 14 plus 11, you get 25, okay, and so on. So that is cumulative frequency. Okay, and then you can see this, the total number of score is actually, sample is actually 40, meaning to say the 20th score and the 21st score, the class should be in the class interval 46 to 50, which is over here. Okay, which is this one. So this is your median class interval. All right. So your L would be, okay, the lower boundary for your median class will be 45.5 here. So you can take L, this is one. So you know already the N is 40, the total number of sample. F, okay, F is the frequency of the interval before the class median. So this is the class cumulative frequency for the class before the median, which is 14 here. And then F would be 11, the frequency of the median class. Okay, and then C is the width. You just minus any of the class boundaries. For example, here 65.5 minus 60.5, so you can get 5. So you just calculate, put the value into the formula. Okay, 45.5 plus 20 minus 14 divided by 11 times 5. So the median is estimated 48. So it should fall into the same interval. So 48 is in here. So if you can get that value in the class boundaries or the class limit, meaning you have calculated the estimated the median correctly. Okay, so the calculation will be not the emphasis on this course, because this is not purely statistic. It's just about how to calculate it. If you can calculate, the most important part is you be able to interpret the meaning of the values. Okay, for example, you can, if you already calculated the mode, median, and mean for your class test, okay, test or your assessment, then you can get there, which is your mode is lesser than median, and then the median is lesser than mean. So if you look at the distribution here, so mode here, median is in the middle, mean is always over here. So always remember that we call median for a reason, because it always in the middle between the mode and the mean. Okay. So in this situation, you can say that you say here the mean. Okay. All right. So the mean is here, average. So the median here, and the mode here. So mode mean the most the score with the most frequencies. Okay. So here the score of the most frequency is lesser than median and mean. So in this situation, we can interpret that many students or many scores are lower than the mean score. Okay, there are a lot of them. It are lower than the mean and median. So we can say that the candidate's performance is low. Okay, total candidate's performance is low or poor, or also we can say that the test is too difficult, or the candidates are very weak. Okay, compared to the test itself, because of the mode. So you should look at the mode in comparison with median and mean. Okay, some situation you can get this where the mode is more than median and mean. Okay, so you can say that the candidates, most of the candidates get score higher than the mean score or the median. So meaning to say, you can say that, you can interpret that the candidate achievement is good, or it also can indicate the test is too easy, or the candidate is very smart, smarter than the test itself. Okay, so that interpretation between these values, the mean, median, and mode. So always remember, median is in the middle between mean and mode. So you look at the mode. Okay, if the mode is greater than both median and mean, meaning to say more higher score compared to the median and mean. If you have a mode lower than mean and median, it tells you a lot of score are lesser than the median and mean. Okay, so that is the measure of central tendency. Okay, while you also need to have the variability measure. So what is this measure? Okay, so it's not complete if you just report the mode, median, and mean. So it need to be reported with the measure of variability of the distribution. So there are many measures for variability, okay, which is always to indicate the difference or the diversities of the score, okay, in comparison of the focus or the tendency of the score. So variability is always, we can use that to tell us the indication, the concentration of the data distribution, where whether it's scattered or is being very focused. Okay, for example, here you have three distribution here. Okay, you have three distribution here with the same number of sample with the same value of mean. Okay, since the variability or the scattering is different, you can see that they are actually different distribution. Okay, so the 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 sample are different in a way that they are not telling us the same information. Okay, so the measure of variability is very important to tell us the behavior or the how we can interpret the data later on. Okay, so I'm going to only discuss about variance and standard deviation, because not only this, but this measure of variability is usually being used the most, mostly used in the interpretation. Okay, so what is variance? So usually variance can be understood by defining it as the mean sum to the sum of squares of the deviation of the score from the mean, meaning to say we minus all of the score with the mean, okay, which is representing the distance of the mean, the scores from the mean, okay. And then while you doing the distance will be either in the negative value or the positive value. So to remove the negative value, so we square all of the values, all the difference, so you can get the sum of square there. Okay, so variance is already a good indication how scattered is the data. So large variance indicates scores in the data are scattered from the mean, while when the variance is small, the data scatter is very small or small. Okay, if the variance is 0, that indicate all the values are equal. Okay, all the same. So there is a problem over there also. So it's very abnormal to get a value of 0 variance. Okay, sample variance is usually symbolized with S square. Okay, why is written S there? It is because variance in the Greek letters would look like S. So S here, S square. So by definition, you minus all of the scores that you have with the mean, and then you square them, and you sum of all of it, and you divide n minus 1. Okay, so x bar is sample mean, xi is the ai sample, and the n is the number of sample. Alright, so then you have the standard deviation. So standard deviation is simply defined as square root of the variance. So you get the variance, you square it, square root of it, so you can get standard deviation. So by squaring it, so you have the same we call that the same unit with the original data. Okay, so you have to remember that the variance is the mean square, okay, of the difference between data point with the mean. So you square it. When you square it, so the unit become different. So just to put back to make sure that you putting it the same unit, so you just square the variance. So this is very mathematical, right? So variance and standard deviation is actually the same thing. They are distant, but we want to use the same unit for standard deviation. So normally we use standard deviation. Okay, same thing, same way to interpret variance with standard deviation. So high SD or high standard deviation, meaning the data scattered, large data scattering similar with variance. Big variance mean you can have data large data scattering. So it's much we call this heterogeneous scattering of the data. If you have small value of SD similar with variance, it will indicate a small data scattering. So this is homogeneous scattering data. So how we calculate this? We have to calculate this. This for this example, I calculating it using the actual definition of the standard deviation and also the variance. So what you do is for this score, you have all of these scores, and then you have the mean. You calculate the mean 64. You can calculate the mean. Okay, the mean is 64.9. Once you calculate the 64.9, of course you can get here. Alright, 64.9 here. This is the total, so the mean is 64.9. So what you do, each of the score you minus with the mean. So 68 minus 64.9, you get 3.10. and so on. For example, here 64, so it would be negative. Okay, 64 minus 64.9 will be negative 0.90. So all of these are negative. Alright, you may ask why just add all of this. If you add all of this because of this negative value, so the total here will not actually representing the distance. Okay, we will look at the distance, not the total value. Okay, so after that you square or each of these difference. Okay, 3.10 square, you can get 9.61. If this one negative 0.9, so the square is 0.81, and so on. Then you add all of this, and then you can get the total sum. The total of it, the sum of square, is 271. Alright, once you get that, 271 divided by 10 minus 1. So the standard, the variance is 30.11. Okay, so once you get 30.11, you square S the variance. So you find the square root for 30.11. So you can get 50. You can get 5.49. So this is the same value, same unit with from the original data. Okay, so that's your standard deviation. Okay, so sometimes standard deviation is written as say S here, or sometimes it's being written as SD. Okay, if you have a, of course, if we have this type, okay, this is maybe you have the same feeling, you hate this one. So same thing. Okay, you just look for the middle point. Okay, from the class limit here. Then you find the fx. The time you multiply 40 with the midpoint. Here is 12. So you can get f here. So you add all the fx. You can get 1815. Okay, so you find the, if you want to look for the average mean, okay, so if you can get the average is, or the mean is 18.15, because you divide 1815 with 100, so you can get 18.15. So you just minus all of the midpoint with the mean calculated. So 12 minus 18.15, you can get negative 16, negative 6.15, and so on here. So you just minus the midpoint. Okay, so you add all the, you square of the difference. Okay, x with minus x bar here. So you square them, then you add all of it. Okay, okay. So this one is only one. So don't forget to time 37.8 here with the frequency. Okay, so this one is only one. Okay, only one of it. So the frequency is 480. So you have to times this square this value with the value of sorry, not this fx, this one 40. So 40 times 37.8. So you can get 1512.9. Okay, so this one, once you get the difference between the middle point with the mean, so you should get negative 1.15. You square it 1.3. So 1.3 times with 25, you get 33.1, and so on. So you add all of this, you can get 4,042, 4,242.8. So you get that sum of square. So you just divide 4,242.8 with 99. So the estimated is about 42.86. So that is the variance. So just square this one. Look for the square root here. So you can get 6.55. Okay, so we have the standard deviation already. Okay, so why you want to calculate all the variance and standard deviation, especially the standard deviation? Okay, because we want to look for the standard scores. So the standard score, okay, but why you want to use this standard score? Okay, for example, here say students get 90 marks on the music test and 40 marks for on his English exam. So if you want to compare this directly, we cannot say for certain how the students is actually performing in comparison between the music test and English test or exam. Okay, because both of these tests are not the same nature, okay, and not from the same distribution. Okay, both marks are not from the same distribution, so you cannot directly compare this value 45 and 90. Okay, so what you will need to do is to standardize the marks. Okay, you have to standardize this 45 and the 90. Okay, so we call that standard score. So this standard score, we need to use the standard deviation. Okay, so standard score is actually how much in standard deviation of the data value is above or below of the mean particular value deviation. Okay, so if you get the standard score is 0, then the value of the data is equal to the mean. So the common standard score is Z score or T score. Okay, normally we use Z score, but sometimes you can get negative, so it's better to use T score. So this is the formula for Z score. So Z is equal actually the value X on the score X minus with the mean X bar divided by the standard deviation. Once you get the T score, you assume the mean is 50. So you time X minus X bar divided by S times 10. Okay. So you can get here actually this part is actually Z. So 50 plus 10 times Z. Okay. So this is an example. It's easier to learn from example than just looking the definition. So for example here, a student scored 65 for the calculus test with a mean of 50, and from that test the standard deviation is 10. Okay, and this student scored 30 for his history test with the mean of 25 and standard deviation 5. So it looks like that this student perform better in calculus compared to the history test. So you need to confirm that by standardizing the scores. Okay, how you do this? You just make this kind of table. Okay, for your calculus, the calculus, the score is 65, the history is 30, and the mean, which is should be given. So the mean is 50, and the history is 25. Standard deviation 10 and 5 here. Then you look for the Z score. Okay, 65 minus 50 divided by 10. So the Z score is 1.5. While the history 30 minus 25 divided by 5. So this is SD. So you can get 1. So you also can get the T score. Okay, T score is about 65 and 60. So you can see that it is confirmed. Okay. Okay, the Z score, the T score for the calculus is larger than history. Okay, it's confirmed that it tells us that the relative position in calculus is higher than the student's relative position in the history. So this we can say that the student is performing better in calculus than in history. Okay, so remember we calculate this standard score when comparing two different distribution. Okay, not from the same distribution. You don't have to calculate this, the standard score from the same distribution. You just compare directly. It doesn't make sense if you do that. Okay, this is another example. For example, here the two different person. Okay, for example, here James and Jenny are siblings. Okay, James scores his mathematics course. James and Jenny is not from the same class. Okay, James score in his mathematics is 65. Okay, and the mean of that distribution is 37.4 with the standard deviation 18. Well, his sister Jenny scored her mathematics 88. Okay, but the mean score for that particular test is 81.2 with the standard deviation of 9.72. Okay, so compare their relative position. So it seems that James is actually at first glance we are going to say, oh, James is performing much poorer than Jenny. So it's not that fair to compare with Jenny because they are from the different class, from different tests, and of course it's from different uh, distribution. Okay, so you just make the same table. So James' score is 65, Jenny's score is 88. The mean for mathematics here for James is 37.4, Jenny is 81.2. The standard deviation is 8 and 9.72 for Jenny. Alright, and then calculate the Z score. As you can see here, 65 minus 37.4 divided by 18, you can get 1.52. While Jenny's Z score is 0.7. Okay, then you can get the T score here is 65.2, while Jenny is 57. Okay, so it seems that actually Z score for James is actually larger than Jenny. Therefore, in the relative position, for James is higher than Jenny. Okay, it seems that now we can see that at the first glance we look like that James is poor, performs much poorer than Jenny, but actually both of them are performing well. Okay, because James' score is 65, and you look at the mean. So James is actually larger than the mean. Well, Jenny is also larger than mean, but in terms of the relative distance from the mean, James is much further from the mean. Okay, much higher from the mean. Okay, so the SD here is actually so 1.52 SD compared to 0.7 SD for Jenny. So actually, James is performing higher than Jenny in their respective class. Okay, so that is how we're going to use manipulate the make use not manipulate make use of the information from standard deviation and also the average or mean. Okay, so this is good to tell us how we can interpret the test result later in your assignment. Okay, I think this is all. So anything you can ask further in the learning management system.